So we've seen the beginning of a dictionary that relates geometry in the form of affine varieties to algebra in the form of ideals. And I want to remind you of the highlights of that so far, which remember stands for Kn. We have so far the following constructions. Given an ideal generated by some elements, f1 through fs, the affine variety associated to that ideal is, by definition, the affine variety associated to that set of generators, which is the common zeros of all those functions. And that's an affine variety. And we've discussed how this doesn't depend on the choice of the finite generating set. We've also introduced a procedure for going the other way, for taking an affine variety, not with any other data associated to it. So the affine variety is just a set. It doesn't come with the information of these functions that were used to cut it out. So just given that set, we can define an ideal, I of v, which is the ideal of all functions that vanish everywhere on v. It's meant at this point to be, you should be a little bit discomforted by the fact that you don't know that's finitely generated, right? So at the moment it seems possible that you could start with a finitely generated ideal, take its affine variety, take the associated ideal, and somehow get something that does not have a finite generating set. As far as you know, that's possible. In fact, it's not, but you have no reason to feel comfortable on that front right now. In part because this procedure of doing v and then doing I may lead to something bigger. If you start with a set of polynomials, f1 through fs, take the associated variety, take its ideal, it definitely contains all the original polynomials, but it may be bigger. And finally, a VW are affine varieties. And then Kenneth spoke about the following fact, that V is contained in W if and only if the ideals are contained in one another in the opposite direction. If the reversal here of direction is a bit of a surprise to you, it's worth thinking through why this is true, so that you this kind of reversal of direction under the passage between geometry and algebra is kind of universal, and this is a case in which it's worth thinking it through. Okay, so that's the story of the relation between algebra and geometry so far. In case it isn't clear, this is on the geometry side, and this is on the algebra side. We've also looked at the division algorithm, and you've been getting your hands dirty a bit, working with polynomials and doing some of the exercises. But hopefully you've got enough of a sense now for the following question to resonate a bit. You might be sitting there doing those calculations and wondering the following: is this algebra, all this algebra, really geometry? I don't see any geometry. There's no pictures here. I'm just shuffling polynomials around. The answer is yes. And in some deep sense, your idea perhaps that geometry is more about those pictures than about the algebra is wrong. So arguably the real core point of geometry lies exactly in those algebraic manipulations. This is a view that will take some time for you to abstract out and feel comfortable with. I doubt that you probably agree with that right now, and that's okay. But we're going to start to see in today's lecture how all that shuffling, those algebraic manipulations you're doing to polynomials, where the geometry lies in there and how to see it. Okay. So I want to build my way up to talking about monomial orderings, but they're a bit of a technical definition, so I'm going to do it in a way where hopefully you see the core point before I have to tell you what it is. So we're going to start with a couple of lemmas that are useful, but really aren't exactly on the topic of today's lecture in some sense, but they allow me to make the point I want to make. And this is something we've used before, and I might as well prove. So let f be a polynomial in one variable, x, and let a be a scalar. Then f vanishes at a, that is, evaluated at a, it gives 0, if and only if the polynomial x minus a divides f of x. Well, we've discussed this before, I'll just remark on it one more time. We sometimes write f with x in brackets and sometimes just f. Those denote the same thing, namely a polynomial. And it's just in this case that we maybe want to name the polynomial that's involved. Maybe now that I think about it, I'll just change my mind here. Suppose that x minus a divides f. That is, f can be written as q times x minus a. Well, then of course a vanishes because evaluating f at a is q evaluated at a times a minus a, so that's 0. So one direction here is clear. Now supposing that f vanishes at a, how do we prove that x minus a divides f? Well, this is a division problem, right? So by Euclidean division or polynomial division, we can write f in this way. I guess it's a bit of a strange thing to call it Euclidean division, given that there are no polynomials in Euclid, but I think you know what that means, right? It's the same algorithm for polynomials as it is for integers, and that algorithm is in Euclid. So we can write f as q times x minus a plus some remainder, where, as Matt pointed out to me just now, either r is 0 or the degree of r is less than the degree of x minus a, which is 1. The point here is that you shouldn't write degree of something is 0, although that's a temptation that's hard to resist. Okay, so either r is 0 or its degree is less than 1, meaning its degree is 0, meaning that it's a scalar. Well, substituting again, x equals a, we have that f, for the same reason as before, that first term vanishes, and I get r evaluated at a, but r is a scalar. Evaluating it at a doesn't do anything, so that's just r. But by hypothesis, f of a was 0, so this means that f is q times x minus a, so x minus a divides f. All right, in some form we kind of expected that argument to be a bit familiar. It's covered in most introductory calculus classes, for example, and this is the reason if f has m distinct zeros, then it's divisible by x minus a for m different a's, and therefore the degree has to be greater than or equal to m. And you've used that a few times already. We have. Okay, so that's the one variable case. I want to now talk about doing this in multiple variables. I'll just check the chat. I see a lot of activity in there. Contravariant. Okay, I'm not even going to try. Yeah, all right. Let's take a point in AN, and let's look at the ideal of that point. A point is an affine variety. That's something we discussed briefly. It's one of the exercises, so this is allowed. I claim this is the following ideal. And this connection between points and ideals of this form is a very important part of algebraic geometry. All right, so let's prove it. The inclusion this way is clear, right? To prove that this belongs to this, I just have to prove that this polynomial vanishes when I substitute p, so to speak. That is, I put x1 equal to p1 and x2 equal to p2 and so on. Well, clearly that's true, right? p1 minus p1 is 0, and so on. Okay, so that inclusion is clear. So we have to prove this direction. That is, we have to suppose that we're given a polynomial which vanishes at p. And we have to prove that it can be written as something times this polynomial plus ... something times this polynomial. So clearly, following the strategy of the previous lemma, we should just kind of divide those polynomials into f, except, first of all, there's more than one of them, and secondly, they're in more than one variable. But we've seen an example already of doing this, essentially, right? We can just divide the first polynomial, x1 minus p1, into f, pretending the rest of the variables are just kind of like numbers. And then when we're finished with that, we can divide by the second one, and so on. And that, in fact, will work. Now, the main reason I want to give this proof is because I want you to see how it works and to think with me through why it works and how we might arrange for something like that to work in greater generality. All right, so I'm going to collect terms to write f in the following form: as a polynomial in x1 with coefficients, I think I will want the degree later, yeah, with coefficients which are polynomials in the rest of the variables, that's x2 through xn. All right, so now we run the division algorithm on f, dividing by x1 minus p1, treating x2 through xn as scalars. I think you have no trouble following what I mean by that. But if you think about the algorithm, you never divide by anything except by the leading term of the thing that you're dividing in. So in the division algorithm, you multiply and you add, and all those things we can do with polynomials. The only place where you divide by something, which is what we couldn't do if the thing we were supposed to divide by was a polynomial, because we don't have the inverse of a polynomial in our polynomial ring, that comes from the leading term, so to speak, of the divisor, which in this case is a 1. Okay, so we'll go through how it works, but you should be prepared to believe it's okay based on that. All right, well, the first step is to write out f as x1 to the n. I'll just write g1 now. Sorry, gn. x1 to the n, that's the highest term, gn minus 1, x1 to the n minus 1, and so on. So in the division algorithm, we should subtract something times x1 minus p1 in order to cancel that leading term. Right, so clearly what we're going to subtract is gn x1 to the n minus 1 times x1 minus p1. Because then this times this will give us exactly the thing we need to cancel off. Alright, when we do that, what happens? Well, the first term cancels. The second term there, if we expand out those brackets, is gn x1 to the n minus 1 times p1. Right, so what do we get? Well, collecting the coefficients of x1 to the n minus 1, we get this. Keep in mind that gn and gn minus 1 are polynomials, but in the x2, x3, xn variables. Okay, so that's what we're looking at. And then we do the same thing to subtract off the leading term of that. Right, so we subtract gn minus 1 plus gn p1 times x1 n minus 2 times x1 minus p1 from this. Why? Well, all this times this will give me this term, which is the thing I want to cancel off. And then this times this will give me some other term, which will mess with the coefficient of the next term down here, and so on. But I don't care about that. I just want to kill off this leading term. Okay, and continuing in this fashion. Notice there was no dividing here because the leading coefficient of x1 was 1, so I didn't need to get rid of that in any way. Okay, so continuing in this fashion, we eventually obtain f. So I keep, so I'm going to subtract this from this, so I'll have f minus something times x1 minus p1 minus another something times x1 minus p1, and I'm continuing like this, grouping all those terms together. I'll get f minus something times x1 minus p1. Undo limit. That's what the attention pen is for. Alright, so f minus q times x1 minus p1, q being the sum of all these things in brackets here, is going to be r. And what can I say about r? Well, r's where the algorithm stops, the thing I can't do anything more with. That is, I should think now about which powers I'd be unable to get rid of. Well, any power greater than or equal to 1 I can get rid of, because the thing I put here is just whatever I need to multiply x1 by to give the next power that I'm trying to cancel. So I can cancel out or subtract away anything with a power greater than or equal to 1, which means that what I'm left with must have no x1s in it at all. That is, r must be a polynomial in x2 up to xn. Apart from that, I can't say anything about it. So usually in the division algorithm, the thing that you're tracking is the degree. I didn't phrase it that way. I just talked about powers of x1, but obviously I could have said the x1 degree is decreasing by 1 in each step, and eventually it gets to 0, And if something has x1 degree 0, then it must contain only the variables x2 through xn. I want to avoid using the word degree because in a moment, well, there's more than one variable here, so the degree is unambiguous. I have to say x1 degree, something like that. All right. Okay, so hence we've written f as, let's call it q1. q1 x1 minus p1 plus something, which is a polynomial in only the variables x2 through xn. So I'm going to do this again with x2 minus p2 and so on, but I'll pause here for questions. Is everybody with me so far? Okay. All right, so now apply the same algorithm to divide x2 minus p2 into r. That is, write r as a polynomial in x2 with coefficients in x3 up to xn. Divide by x2 minus p2. Eventually you'll reach a remainder that has x2 degree 0. That is, it only involves the variables x3 through xn, and so on. And then we can divide x3 minus p3 into that remainder, etc. And eventually we'll be able to write f as a sum of some polynomials. Who knows what variables they contain? Might like to think about what's in there. Plus a lambda. What's in the final stage where we're dividing xn minus pn into that last remainder? Eventually we get down to something that has xn degree 0, but it also doesn't contain any of the earlier variables, so it must just be a constant, a scalar. All right, it's kind of unfortunate to get to exactly here on this set of boards. Let's see.
You could use a personal board.
Yeah, then that'll be minuscule in the recording. I think I'll just shove it on this previous board. It's not awesome, but well, it'll fit over here. Okay, so we're going to finish the proof in this tiny box. I think you should see what we're about to do, right? So what was our original hypothesis? We assumed f of p was 0 back at the beginning. Well, if I substitute p, that is x1 equals p1 ... xn equals pn, into this final formula, then I get 0 is fp, and xi minus pi all vanish at p, so that will just give me fp is 0 plus lambda. Okay, so lambda is 0. That means that looking at this expression here, I've shown that f belongs to that ideal. So I'm done. Okay, so now what I want to do is think through that. Well, that is an example of a division algorithm with more than one variable. In some sense, it was a little fake because each variable got treated in its own round of division and they didn't interfere with one another. But that last part, that they didn't interfere with one another, is the thing that's really interesting. So why did this succeed? Why, when we proceeded from kind of stage to stage, from x1 to x2, from x2 to x3, and so on, did each stage not undo the progress that was made in the previous stage? Why at each point here was I somehow making progress? So I want to think about that a bit. But before I do that, are there any questions about the proof? Okay, well, while you're thinking, we'll move over to the next set of boards. Okay, some observations. Of course, there was nothing important about the fact that we did x1 first. All the variables are on an equal footing. I could have done x2, that is divided by x2 minus p2. I could have done that first and then x1 minus p1, or in any order I liked. So that didn't really matter. But we did choose an order, right? So that's something that's worth noting. We chose an order, namely we did x1 first, and then x2, and then x3, and so on. So right now this doesn't have a formal meaning, saying x1 is greater than x2. All I mean by this is that in the division algorithm we prioritized x1. Now if you think about it as n different phases, where in the first phase we divide by x1 minus p1 and then so on, that's fine, except you could think about it as one global operation. It's just that as long as any x1s remain, we hunt them down and destroy them, and we don't worry about x2. That would have the same effect, right? We would sit there, we would look at the polynomial. As long as there are x1s, we keep dividing by x1 minus p1, and we don't stop until we've gotten rid of all of them, or at least as far as we are able. In the above example, we could get rid of all of them. That's what I mean by x1 being greater than all the other variables. It has highest priority. Okay. Now what made the proof work was that once we were done dividing by x1 minus p1, later stages in the algorithm never reintroduce x1s. Right? Once we've prioritized x1, we've removed all of them. Then when we're working on x2 or x3, we don't accidentally reintroduce an x1 that we'll have to go back then and get rid of again. Right? We can move through these stages in order, knowing that the previous ones remain complete, so to speak, while we're doing the later ones. So that was important. And I want us to look at the actual algebra to see why that was. I mean, it's kind of clear, I think, in this example, but I'm going to complicate the example a little bit so that it becomes a little bit more interesting. Okay, so let's go back to that algebra a bit. So let's look at our polynomial. So this is the f that we had before. So in the first step, we got the remainder all these intermediate remainders are called dividends, which was f minus this. Right, so that gave me this. And then the next term didn't change. That was just as it was in f. Okay, so what I'm saying up here, a particular case of that, is the fact that this contains no x1s. Right? This, of course, contains no x1s. I mean, the GIs, remember, were defined to just be polynomials in x2 through xn. All right, well, we have... So I want you to point out to me a way in which we could do this more generally. So why do we know that coefficient? doesn't involve x1s, well, P1 is in K. But we could be a little more relaxed about our hypothesis on P1, right? So what could P1 be more generally and still have this be true, that this new coefficient of the leading term of the remainder is a polynomial in the x2 through xn variables only. Of course, in the lemma, the PIs are scalars, but I could do this division algorithm with a more general polynomial, x1 minus p1, and I'm asking you, what more general thing for p1 would still work at this point? Okay. Well, even if P2 were a polynomial itself, I mean, that would still be true, is what I mean. Okay, so if I have a polynomial f, I organize the terms, I divide x1 minus p1 into it. No matter what p1 is, I'll write down what I wrote down, as long as it doesn't involve the x1 variables. Everything I wrote is still fine. That coefficient of x1 to the n minus 1 over here is still in the polynomial ring x2 through xn. Now, if P1 contained x1 variables, this would all break, right? First of all, maybe if P1 contained x1 terms of higher degree than this, I shouldn't do the division in this way, because if P1 contained an x1 squared, for example, there'd be an x1 squared here, and overall, this term would have a higher degree than n. So the degree of x1 wouldn't even be going down as I try to do my division. And if the degree of x1 doesn't go down, then why should I ever finish? What's the point? What am I doing? So clearly I want, okay, if there are no x1s in P1 at all, then everything's fine.
And you're at P2 there.
Did I?
You meant P1, I think, the last line.
Oh, thank you, yeah. Okay, but P1 involving the x2 variables is fine. Nothing bad will happen there. Okay, let me point out that we could also divide by x1 to the I'm going to call it k. Yeah, I realize this is an abuse because k is the field, but these are different types of things, so usually we allow this. So you could also divide by this polynomial as long as the x1 degree of P1 is strictly less than k. Now what do I mean by that? I mean that no monomial of P1 contains a power of x1 which is equal to k or greater. Now, of course, we're now moving past the setting of the lemma, but I want to imagine f looks like it does on the previous board, and I just try dividing this thing, x1 to the k minus P1. So P1 is now a polynomial. And suppose I try dividing it into f. Well, what will I do? I'll just write down the same thing, right? I'll take f, I'll subtract whatever I need to multiply that by to get x1 equal to the leading term. But now that's not n minus 1, it's n minus k. to assume that's less than or equal to n. And when I do that subtraction, I'll get the same thing that I got before. P1. Okay, so the first term will cancel from this, and I'll be left with plus gn x1 to the n minus k times p1. Well, sorry. Yeah, maybe I should write this out. Okay, now I need to pay a bit more attention to this term, right, which came from this product here, because P1 may contain, this may contain x1s now. But it only contains powers of x1 with L strictly less than k. So the only terms I'll get out of this, at most they can be, so P1 x1 to the n minus k contains powers of x1 are less than, so this can contain powers at most x1 to the k minus 1. So well, strictly less than n. So I don't know why I wrote that. Okay, so this is going to cancel that. And whatever comes out of this product here, it'll only affect the coefficients. I can regroup the terms, and it will only affect the coefficients of x1 to the n minus 1 and lower. Okay, and I can still keep those coefficients by regrouping terms as polynomials in x2 through xn. But this works because the degree of x1 went down. So then I can do it again. I can do it again, and eventually I'll get down to an x1 degree. It may not be 0, because I can't necessarily get down to 0. As soon as the degree hits k and drops below k, then I can no longer divide by x1 to the k minus p1. I think that's familiar. So we can continue. Until the remainder in the last step has x1 degree less than k, and then we have to stop. But then if I had another polynomial, say x2 to the L minus p2, so we can then divide by that and so on. Okay. So everything would work as long as P2 didn't involve x1s anymore. And that should have x2 degree less than k. Suppose we got to this last remainder for the division by the x1 to the k minus p1, and we started dividing by x2 to the L minus p2, where p2 contained x1 variables. Then, as you can see in the algebra on this board, we would reintroduce x1s somewhere, right? in this step, for example, where there's a green. So in this step here, if this was a P2, we'd be reintroducing x1. And then we have to go back to the first stage again. Right? So as long as there's no x1s here, we'll be fine. Okay, so I'm going to do the example, the exercise, I think it's 1.4.12, to show you how this works in practice. And then we're going to systematize all of this. So this is as messy as it's going to get, and I'm going to now say some more abstract things. But I hope the strategy here made a bit of sense. So there were two things that we were trying to simultaneously decrease. We're trying to decrease the degree of the active variable, in the first case x1, getting it down as low as we can, below k, in the last setting of x1 to the k minus p1. And we're trying to eliminate earlier variables, right? So there's two things we care about somehow: powers and which variables. And we want to arrange it so that we can make progress, so that this algorithm eventually terminates. Okay, so I'll show you what this looks like in an example. Feel free to ask a question, obviously. All right. So what do I mean when I write something like x is greater than z is greater than y? So such a thing is called a monomial ordering. All right, so throughout all of this, k is a field. We know monomials in our polynomial ring can be identified with the exponents, which are tuples. And recall that n for us means what sometimes, and what the book calls z greater than or equal to 0, non-negative integers. And we're going to freely switch between monomials and these exponent tuples as we wish. And we're also going to write EI for this particular tuple. So x to the EI is what we might call xi. All right, so I want to remind you that a total order on a set S is a relation which is not reflexive or irreflexive, which means for all S in S, it is not the case that S is strictly less than S. I say strictly less than, but this is just some English gloss on a particular relation, which is written in the same way we write the order relation on integers, but it's just a general relation. It should be irreflexive, it should be transitive. That is, for all S and T, for all ST and U rather. If S is less than T and T is less than U, then S is less than U. And most importantly, it's total. That is, for any pair in S, we have S less than T, or S is equal to T, or S, I'll write it like this, or T is less than S. As usual, we write S greater than T if T is less than S. That's our relation, but we allow ourselves to write this other symbol to mean that. And S less than or equal to T means S is equal to T, or S is in the relation with T. Okay, so our monomial order, or monomial ordering, usually written strictly less than with some subscript on our polynomial ring, is a relation on monomials or on tuples, same thing, satisfying the following conditions. It's a total order. Secondly, it's compatible with multiplication, which is to say if alpha is greater than beta. If I use Greek letters, I mean tuples. And gamma is another tuple, then alpha plus gamma is greater than beta plus gamma. By the addition here, I mean coordinate-wise, so you add them as vectors. Of course, that's the same thing as saying x to the alpha. So our hypothesis was x to the alpha as a monomial is greater than x to the beta, and adding exponents means multiplying monomials. So this is the same as saying this, that if you have an order relation between monomials and you multiply both sides by any monomial, you have the same relation. Finally, it's a well ordering. That is, every non-empty subset S has a smallest element. What I mean by that is there exists an S in S, such that for all t in S, S is less than or equal to t. All three of these we can see why they sort of arose out of what I was discussing earlier. So I won't belabor it any more than I already have, but I suggest to you to go back and take a look at where we use this once you've sort of processed how the order relation plays a role there. It's got to do with when you take, say, x1 minus p1 and you multiply it by something in order to match up the leading terms, the sub-leading term in x1 minus p1, namely p1, doesn't beat the leading term after you've done that multiplication. They maintain the same order. Otherwise, when you were dividing polynomials into other polynomials, the order of the monomials inside the divisor would get messed up when you multiply it by what you need to multiply it by to try and cancel out the leading term. And then we wouldn't be able to progress in the division algorithm. So that's a comment that may not make a whole lot of sense to you now, but hopefully it will in a bit. The well ordering, that's clearer, I think, because I was emphasizing several times the idea that we need to make progress. That is, the termination of the division algorithm is what we want. And to say something is a well ordering is equivalent to saying that descending chains are finite, which is clearly what we want if we want to make progress in the division algorithm. That'll be my next lemma, so let's not worry about that too much for now. Okay, so I'm going to give some examples, obviously, and state some lemmas, and prove a little bit. I want to remark at this point that we do not define an order relation on general polynomials, except insofar as we say something like the leading term of one polynomial is greater in the monomial order than the leading term of another. That's fine. Or leading monomial is greater than the leading monomial, rather. But we never directly talk about something like f greater than g for f and g general polynomials. Okay, so it's just monomials that we compare. So let me define our first example of a monomial order. It's kind of what you might think is the normal one. So we define alpha to be greater in what's called the Lex order, or lexicographic order, if the leftmost non-zero entry of alpha minus beta is positive. I.e., we have something like, at the beginning, potentially some of the alphas are equal to some of the betas, but the first time they're not equal, so maybe I should write it like this. The first time they're not equal, the alphas win. And then who cares? Maybe later on the alphas are smaller, but the game's already over because the first one to be greater than the other wins. Okay. So this is called lexicographic order. It's kind of alphabetical order for words, right? Or lex. Well, remember we either order tuples, so in Lex order, of course this tuple beats this one, because while they're never equal, just in the first position, the left-hand one is greater than the second-hand one, and that in turn beats this, and so on. So in terms of variables, that means x1 is greater than x2 is greater than xn. I want to emphasize that x1 beats any power of x2. Right, x1 is not impressed by a strong effort in exponents in any later variable. It doesn't matter. X, as long as there's a single x1, it beats anything that involves smaller variables. Okay. Yeah, forgive me. I'm just going to erase this now. I think that point is made. In order to fit the lemma on here, I want to keep the definition on the same screen. Well, we haven't proven that this is a monomial order, right? That's a definition. It's easy to see that it's transitive and total, but I need to prove these two other conditions, 2 and 3. 2's clear, I'll prove it in a second. 3, however, well, why should every subset have a smallest element under this order? Maybe take a minute to think about it. What I'm going to do is I'll prove it, but I'll prove something slightly different but equivalent, and I want to prove that equivalence first. It's just a different way of thinking about a well ordering. So a total order on n to the n is a well ordering. If and only if every strictly decreasing sequence is finite. Okay. The book gives an argument that has one of these hidden applications of the axiom of choice that kind of drive me nuts. So I'm going to write something a little bit different to what the book says, just to make clear that there isn't actually any secret choice here. So suppose it's a well ordering, and that we have a sequence which is not strictly decreasing perhaps, but decreasing. This is a sequence, in case it wasn't clear. These are elements of n to the n. It's not important that the set is n to the n, as will be clear, but that's what we care about, so that's what I'll say. So suppose we have a decreasing sequence. Well, then as a set, that's a subset of n to the n. It's not empty. Therefore, by the well-ordering condition, it has a least element. And that element is alpha n for some n. And clearly then, since alpha n is less than or equal to all the other alpha i's, and we have the other relation by transitivity, we must have that alpha I is equal to alpha I plus 1 for all I greater than or equal to n. Okay, and that proves the claim, right? Because if we were to have strictly decreasing, a strictly decreasing sequence in particular is decreasing, and then at some stage it must stabilize, but that would be that would prove that that sequence has to be finite. Okay, so I just have to prove the converse now. So suppose every strictly decreasing sequence is finite. And I want to prove the well ordering. So suppose I have a non-empty subset. Well, let C be the set of maximal chains that look like this in S. A maximal chain just means a sequence where the first thing is greater than the second thing, and so on, and it can't be extended at either end. That is, I can't make this bigger, and I can't make it bigger on that end either. So C is the set of all such things. This is non-empty, because we can take any element of S. S is non-empty. And if it's not minimal, that is, if there's something strictly smaller than it in S, well, choose one. And just keep doing that. By hypothesis, you'll finish in finite many steps, right? Because every strictly decreasing sequence is finite. And then you can do it in the other direction as well. Actually, I don't need maximality in both directions. So let me say downward maximal. That is, take chains that can't be extended at the bottom. Okay, and this procedure I just outlined constructs such a thing starting with S. Okay, so this set C is non-empty. Yeah, well, it's not the axiom of choice. This choice is not real choice. This is mild choice. Because you see, I'm just proving the existence of something. I'm not... if you look at the argument in the book, you sort of have not a single choice. You're actually making choices based on previous choices in a way that seems to invoke the axiom of choice. I don't want to dwell on that too much, but yeah, that's maybe something interesting to think about. Okay, so C is non-empty. And note that if I have two things in C, well, those endpoints have to be comparable. Right, so either alpha n is less than beta m, but this contradicts that chain beta being maximal, right? Because the whole idea was that this couldn't be extended further, but if alpha n is in S and is less than beta m, I could have extended it further, so that's a contradiction. Similarly, I can't have alpha n greater than beta m for a similar reason. The alpha chain is maximal. So the only other possibility is that they're equal. Okay, so those three possibilities, two of them lead to a contradiction, so it must be the third one. So that is, every maximal, downward maximal chain in S has the same ending point. And this common final entry is a least element of S. Why? Well, take any element in S and construct that downward maximal chain that starts with it, as I did earlier, that finishes somewhere, and by what I just said, that somewhere is the same element that works for every element of S. So that's a minimal or least element. Okay, maybe that was a little bit technical. It's not too important. This technique is not something we're going to use again. Okay, what it means is that if I say that if you want to check that a monomial order is a well-ordering, the third condition in the definition, then you just need to think about proving that every strictly decreasing sequence is finite. So let's check that for Lex. I think we're going to move around to the next side of the board, so follow me, please. Any questions?
I have a question, actually.
Yep.
In the argument, so we looked at the smallest elements of the both, how you call that?
Chains.
Chain.
Yep.
But like, okay, it's not going to prove the result, but what happened if we looked at the other side of the chain? Like, can't we make a similar argument to prove that the actual, like the leftmost are actually equal, and then maybe like the wall chains are equal? Like, it feels weird to me.
But our hypothesis was that downward chains are finite. Okay, if you take an infinite chain going up, so alpha 1 less than alpha 2 less than alpha 3, ...
Yeah.
Every finite part of that is a downward chain and is finite. So the hypothesis that downward chains are finite doesn't give you that upward chains are finite. Although any finite downward chain, I mean, is the same as a finite upward chain.
Okay. What I meant is that, like, so we assume. Okay, let me check. Sorry, I'm on my phone, so it's kind of hard for me to
Sure.
check things. But so yeah, we said assume we have sorry. We've proved that Oh no, okay, downward maximal chains. Oh, yeah, it's downward. It's just downward maximal, like not maximals in both
That's right.
directions.
Yeah.
Oh, okay, sorry, I missed that. Okay.
Yeah, that was my notes say something else, but that's what I meant to say. Yeah.
Okay. Thank you.
Yeah. All right. So let's prove that Lex is a monomial order, and we'll state a few little properties, and then that's what we'll finish. So proposition. This is a monomial order. So we have three things to prove. The first says that this is a total order. I'm just going to skip that. It's easy. I think it's something you should think through, but it's not really worth our time together to do it. The second says that if I have this relation and some monomial gamma, then alpha plus gamma is greater than beta plus gamma. And that's true because to compute that whether alpha plus gamma is greater than or less than beta plus gamma, what I'm going to do is I'm going to take the left-hand side, I'm going to subtract the right-hand side. I'm going to look to see if the first non-zero entry is positive. But that difference, I mean, this is just adding coordinate-wise, so I can just use ordinary algebra to cancel off the gamma. So that's just alpha minus beta. So looking for the first non-zero entry here is the same as looking for it here. Okay, so 3 is where the action is. All right, so we use the lemma. So I'm supposed to, therefore, consider a descending chain in Lex order of monomials. And I want to prove that it's finite. Okay, that there can exist no infinite descending chain of this form. Let's pay attention to the first entry in each one of these tuples first. So there exists an n1 such that for I greater than or equal to n1, those first entries stabilize. That is, they are all equal. Past a certain point. Why? Well, since alpha I is greater than alpha I plus 1 in Lex order, either, I mean, the first entry, we don't have to worry about any previous zeros, right? So either those entries are equal, or the first one is greater than the second one. Okay, so if you pay attention to the first entries in all these tuples, they only ever go down. And there's only finitely many times they can go down, since alpha 1 is finite, and these numbers are non-negative. So if I look along this entire chain, there are only finitely many steps where it goes down, which means that at some point it must just be all equalities. All right. Now go to that point at which, past which these are all equalities in the first position. and then apply the same logic to the second position. Now past n1, we don't have to worry about the first positions anymore, right? Once we get down to alpha n and past here, the first positions are all equal, right, by definition of n1. So when we're comparing them in Lex order, we ignore the first position and we look just at the second position, and then the third if they're equal, and so on. Okay, so applying the same logic to the second position, we can find an n2 such that alpha I2 is equal to alpha I plus 1, 2 for I greater than n2. Okay, so proceeding in this way, that is proceeding by induction on the position, we can find a single n that works for all of them. And if the tuples are equal in every position, then they're equal. So we're done. Eventually that sequence, well, that's a contradiction, I guess, rather, right? I suppose they were strictly greater. A contradiction unless the sequence is finite. The contradiction being that at every point I assume that the tuples were distinct, right? Because that's a strict inequality. Okay, so Lex is a monomial order. I want to finish with the definition of leading terms, leading monomials, and so on. So let f be a polynomial. Then. So these are very important terms for the rest of the course. We don't talk about the degree of a polynomial in more than one variable. We talk about the multi-degree. The multi-degree of f is, well, take all the monomials or exponents with a non-zero coefficient in f, or what's the same, take all the terms of f and take the monomials in those terms. And then that's a finite set, and since we're given a monomial order, all of this depends on a monomial ordering. It's not an intrinsic property of the polynomial. So given the monomial ordering, this finite set has a maximal element because it's a total order. And that maximal element is called the multi-degree. So it's with respect to our monomial order. Sometimes this is denoted multi-deg f. I think that's kind of gross, so I'll rarely write it, but okay, so if alpha is the multi-degree of f, what did I forget to say here? As defined, this has a bug.
On 0f?
Yeah, exactly, right. So if f was 0, this set would be empty. And what do I mean by the maximum? Okay. So a non-zero polynomial. All these things are only defined for non-zero polynomials. So if alpha is the multi-degree of f, then the leading coefficient of f is written LC, and it's the coefficient of that monomial in f. strictly speaking, we might write something like LC less than F or something, because it really depends on the monomial order, but it's so cumbersome that we never do that. The leading monomial of F, written Lm, is the x to the alpha, and the leading term of F is that term, Lt. Okay, so leading coefficient, leading monomial, leading term, multi-degree. You just have to remember this terminology. All right. I think I'll probably stop with that definition. There's another lemma in the notes, but it's an exercise for this week, so I think I don't need to write it up. So we'll stop there and open to questions. Thanks, everyone. After the questions, we'll just proceed straight on with the exercise session, and if you come back in an hour from now, we'll have a little bit of a mini game in TRS. So thanks, everyone, for sticking around, and any questions?
Cool. Thanks, Dan.
Yeah, you're welcome.
Thank you.
Thanks, Dan.